Okay, a third video about stability for second order constant coefficient equations. But we'll move on to matrices here. So this is a rather special video. So this is our familiar equation, and I took A to be 1. I just divided out A, no problem. So that's one second order equation. But we know how to convert it to two first order equations. And here they are. So this is two equations. That's a 2 by 2 matrix there. And so let me read the top equation. It says that dy dt is 0y plus 1 dy dt. So that equation is a triviality. Dy dt equals dy dt. The second equation is the real one. The derivative of y prime is y double prime. So this is second derivative here, equals minus cy and minus by prime. And that's my equation, y double prime. When I bring the minus cy over as plus cy, and I bring the minus by prime over as plus by prime, I have my equation. So that equation is the same as that one. It's just written with a vector unknown. It's a system of two equations. And it's got a 2 by 2 matrix. And it's called, this particular matrix with a 0 and a 1 is called the companion matrix. So this is the companion equation to that one. So, okay. So whatever we know about this equation from the exponents, S1 and S2, we're going to have the same information out of this equation, but the language changes. And that's really the point of this video, just to tell you the change in language. So here it is, that the old exponents S1 and S2 for that problem, and everybody watching this video is remembering that S's solve S squared plus BS plus C equals 0. So it's always what our S's are. So that has two roots, S1 and S2, that control everything, control stability. Now, if I do it in this language, I no longer call them S1 and S2, but they're the same two numbers. What I call them is eigenvalues. A cool word, half German, half English maybe, kind of a crazy word, but it's well established. Those same numbers would be called the eigenvalues of the matrix. You see, the matrix in this problem is the same, got the same information as the equation here. So those are the eigenvalues. And may I just tell you what you may know already, that everybody writes lambda, a Greek lambda for eigenvalues. So where I had two exponents, here I have two eigenvalues. And those numbers are the same as those numbers. And they satisfy the same equation. And when we meet matrices and eigenvalues properly and soon, we'll see about eigenvalues of other matrices. And we'll see that for these particular companion matrices, the eigenvalues solve the same equation that the exponents solve, this quadratic S squared and BS and C equals 0. Okay. And stability, remember that stability has been real part of those roots of those exponents less than 0, because then the exponential has that real negative real part and goes to 0. Now we're just using, so that was our old language, and our new language would be real part of lambda less than 0. Stability stable matrix is real part of the eigenvalues, lambda less than 0. So we're just really exchanging the letters S and the single high order equation for the letter lambda and 2 first-order equations. Okay, I'm doing this without just connecting the lambda to the s, but without telling you what the lambda is on its own. Okay, so let me remember. So, here I've taken a further step, because basically I've said everything about a second-order equation. We know the condition for stability. The condition is that the damping should be positive, B should be positive, and the frequency squared better come out positive, so C should be positive. So B positive and C positive were the case when this was our matrix. Now, I just have a few minutes more, so why don't I allow any 2 by 2 matrix? I'm not going to give you the theory of eigenvalues here, but just make the connection. Okay, so I want to make the connection. And you remember that the companion matrix had the special form 0, A was 0, B was 1, C was the minus the big C, and D was the minus the B. That was the companion. So what am I going to say at this early, almost too early moment about eigenvalues? Because I'll have to do those properly. Eigenvalues and eigenvectors are the key to a system of equations. And you understand what I mean by system? It means that the unknown, that I have more than one equation. My matrix is 2 by 2 or 3 by 3 or n by n. My unknown z has 2 or 3 or n different components. It's a vector. So z is a vector. A matrix multiplies a vector. That's what matrices do. They multiply vectors. So that's the general picture. And this was a especially important case. So we can decide on the stability. So I'll just summarize the stability for that system. The stability will be, well, I have to tell you something about the solutions to that system. Remember, z is a vector. So here are solutions. Z is, it turns out, this is the key, that there is an e, you expect exponentials, and you expect now eigenvalues instead of s there. And now we need a vector, and let me just call that vector x1. And this will be the eigenvector. And this is the eigenvalue. And if I look for a solution of that form, put it into my equation, out pops the key equation for eigenvectors. So again, I put this hope for solution into the equation, and I'll discover that A times this vector x1 should be lambda 1 times x1. Oh, well, I have a lot to say about that. But if it holds, if A times x1 is lambda 1 times x1, then when I put this in, the equation works. I've got a solution. Well, I've got one solution, and of course, for second order things, I'm looking for 2 solutions. So the complete solution would also be, so I could have, it's linear, so I can always multiply by a constant. And then I would expect a second one of the same form, e to the some other eigenvalue, like some other exponent, times some other eigenvector. Here's my look-ahead message, that solutions look like that. So we're looking for an eigenvalue and looking for an eigenvector, and there's the key equation they have to satisfy. And that equation comes when we put this into the differential equation and make the 2 sides agree. So that's what's coming. Eigenvalues and eigenvectors control the stability for systems of equations, And that's what the world is mostly looking at. Single equation once in a while, but very, very often a system, and it'll be the eigenvalues that tell us. So are the eigenvalues positive? In that case, we blow up, unstable. Are the eigenvalues negative, or at least their real part is negative? That's the stable case that we live with. Good, thanks.